In this video, you are going to learn about both elimination reactions and condensation reactions. So this should be a fairly short video, but you will have to draw out some of the reactions that we will be using for our mechanisms. So in an elimination reaction, we're primarily talking about a bromoalkane. So think of a singly bonded chain that has a bromine on it. If you warm that with dilute aqueous alkali, so base, something with an OH in it compared to a metal like a KOH or an NaOH, you're going to undergo a substitution reaction to get an alcohol. We've learned that before, and we've learned that those mechanisms are either SN1 or SN2. That's what we've learned previously. But if you change the conditions just a little bit, if the base is very hot and very concentrated, then it's undergoing an elimination reaction to form an alkene. So you're going to take something that had a single bond and eliminate one of those to make it a double bond. So let's look at how that happens. The reaction, or the conditions needed for this to happen. So remember, this first bullet point is talking about something you've already learned, either a substitution reaction by SN1 or SN2. If we want it to be an elimination reaction, the second bullet point, you need it to be that the hydroxide, the base, is dissolved in very hot ethanol, and it has to be heated under reflux. Now, reflux just means, you can Google search this if you actually want to see an apparatus to do this, but a reflux just means that as you're heating this, you are pulling that product off and recondensing it so that you can use it. Now, we're going to look at the reaction that you're going to get. The overall reaction you'll see, you can take any bromoalkane. So I'm going to leave these bonds as being fairly generic. And this is what makes it the bromoalkane. So you could have any number of C chains from this, okay? But what you're going to do is react it with that base, the hydroxide ion. And in this process, what you're going to do is you're going to eliminate the H and the Br from this, and you're going to create a double bond. And then, because the H can bond with the hydroxide ion, you're going to get water as one of the products, and then the bromide ion will be left over. Okay? So that's your overall reaction. But it can happen by two different mechanisms. So the first mechanism is called E1 mechanism. And this has a carbocation intermediate. And how this forms is heterolytic fission. Okay, so heterolytic means that you're breaking it into different pieces. Okay, so I'm going to show you how this works. I'm going to use the same generic halogen alkane that I had before. Only now I'm going to put the H and the Br just on the bottom because it gives me a little bit more room to kind of draw my arrows. Remember, mechanisms always show curly arrows. Now, in this case, what you end up with is this heterolytic fission. So this alkane is not going to split evenly. What will happen here in this very next step, as this hydrogen bond, these electrons are going to go into what will become our double bond. And the bromine that was there will leave, taking its electrons with it. So this is going to be our carbocation intermediate. Now, all of those bonds that were there that we just left as generic linkages will stay. Now, the hydroxide, which is very negative because of the electrons from the oxygen, that's going to bond in here and kind of, it's going to be present. So this part is present, and in the next step, these electrons are going to go to the H. So I'm going to I'll use a different color arrow because this gets kind of confusing, so like this. And then our very next step, what we have formed is our double bond and our water, because the electrons from the hydroxide went to the H, which had left by giving its electrons to the double bond, and then we get that Br minus. Okay, so that's one of the ways. Now it's called E1 because there's one starting molecule here. Now, E2 mechanisms involves both the hydroxide and the bromoalkane. So this one's a little easier maybe to picture. So here I'm going to draw my hydroxide with its electrons. This has a minus charge. And we'll still use the same haloalkane, bromoalkane that we had before. And remember, I'm leaving these other bonds as generic because that means it could be anything. Now, in this process, E2 mechanisms, these electrons are given right away to the H. And that H then says, I'm going to get rid of my electrons to the double bond, which looks the same as what we have up there, only in this case, the difference between the two is the H, the Br leaves without a reactant molecule there first. In the second mechanism, they work together. So the H is giving its electrons to the double bond, and the bromine is going to leave again, and we'll get a new product. Again, the product of the elimination reaction is an alkene. So I'm going to just, these H's, that H would stay, and these can be whatever they were before, and you still have H2O and Br minus. So the products of each of these are the same. It's just the process by the proposed mechanisms are different. Okay? So E1 involves one reactant molecule, E2 involves two reactant molecules. So that's elimination reaction. That material is just for the higher level students, although everybody should know it for our chapter exam. And then lastly, the condensation reactions. You actually should be familiar with these based on what you watched with your polymers. But in condensation reactions, these are terminal, meaning you're going to have a reactant molecule, something is going to condense out of it, and you're going to get a new product, but it's not going to polymerize. So basically what you have is two reactant molecules that will react together to produce one larger molecule, but you're going to eliminate some small molecule, like usually water or HCl, to get out of there. Now, and a good example of this is making an ester. We call that process esterification. So you're making an ester. Now, to make an ester, you need a carboxylic acid, so a COOH. And by the way, some of you on your labs are drawing those wrong. You have to be very careful. C double bond O, OH, and that's going to react with an alcohol. Now, hopefully you can see where you're able to pull a water out of that and then shove the remaining things together. You need to, in order to make an ester, you need sulfuric acid, concentrated sulfuric acid as a catalyst. And so here's an example of this. Let's start with CH3, COOH. Now, hopefully you guys know now, even though we've always called this acetic acid in our IB1 years, we now know this as ethanoic acid. And the reason it's ethanoic is that there are two carbon atoms in the chain. Now we're going to react that with ethanol. So we want two carbon atoms in the chain. So this is ethanol. Now, what's going to happen here is that we are going to get these two molecules near each other, and the OH from the carboxylic acid and the H from the alcohol, although it really wouldn't matter which ones you pick, are going to bond together to make water. And that's going to be cleaved out of there, and you're going to shove what remains together. So the product of this would be CH3 from your ethanoic acid. The C double bond O stays, but now that OH is gone, and so is the H from the alcohol. So the next thing it can bond to is the O from the alcohol, and then CH2, CH3. And now that product is an ester, and you should recognize the functional group of a C double bond O to an O to another R group as an ester. Now we can actually name this ester. It was formed from ethanol and ethanoic acid, so it becomes ethanoate. And that's an example of a condensation reaction. Now, the only thing we're missing here is that water has to be a product. So that's what was eliminated in this condensation reaction.